Start recording. Okay, there we go. So we are going to be on page 91. This is the last big topic, titrations and titration curves. Last big topic of this unit. It's titrations. Okay. Glove. We've already talked about titrations in the solubility unit. And we have talked about equivalence point. Tell your partner what the equivalence point is.
No, I actually forgot. Oh yeah, equivalence point is when the A plug equals the K. It's not there, but what do you? Okay. Wait, you're not? It's like very little of the shade.
That would be the half equivalence point.
Oh, half.
Equivalence. What does the first part of that word remind you of? Not equilibrium. Equal. What is equal? Same, but what two things are the same at the equivalence point? Or what is equal at the equivalence point? Oh, actually, I should say in an acid-base titration.
Both of these are neutral. It's like it does the equals the neutralization reaction. Multiple concentration.
It's where the moles of the acid equal the moles of the base. But you have to watch out if you've got a diprotic acid, it's where the stoichiometry is perfectly fulfilled. Okay? Actually, in any titration is where the stoichiometry is perfectly fulfilled. You have no excess of either reactant. You will often hear it said that the moles of acid equal the moles of base, but like I said, if you've got a 2-to-1 ratio, if you have SrOH2 and HCl, and you've only got one H and two OHs, then it's going to be a 2-to-1 ratio instead of 1-to-1. So I can't say that the moles are equal, but anyway, so yeah. So you can find the equivalence point. How would we often signal that we have reached the equivalence point? What would we use? How did you know last year when you did a titration that you had reached the equivalence point? You would use an indicator. So an acid-base indicator can be used to signal the equivalence point. Alternatively, and this is what we're looking at today, the pH meter can be used to monitor the progress of the reaction. So a pH meter can be used to monitor the progress of the reaction. And what we would get from that is we would get a pH titration curve. So we would graph pH as a function of the volume of titrant, which is our standard, which is the one of known concentration, added. So what you would have is you would have a curve where you have, say, volume of NaOH added versus pH. And you can find the equivalence point that way instead of using an indicator. How do you do that? You stick the pH meter into the beaker or the flask. Very often you will put it on a stir plate, which looks like a hot plate, but it's not. And at the bottom of the stir plate, you'll put a magnetic stirring bar. And so we have, in that beaker, we have some HCl of unknown concentration. What do we have up in our, what do we call that big long tube? That is called a burette. Okay, that is our burette. And it contains NaOH, and the NaOH has the known concentration. What do we call the thing that has the known concentration? That is called the what solution? It's called the titrant. It is also called the standard. It's called standard because it has been standardized. It just means, standard literally means it has known concentration. Okay? That's what the word standard means. And we have the HCl of unknown concentration. Do you remember what we call the thing that has an unknown concentration? It's called either the analyte, because we are analyzing it. Whoops, I can't spell. Or it's called the sample. Okay, the go figure question. In which direction do you expect the pH to change as NaOH is added to the HCl solution? Tell your partner. In which direction do you expect the pH to change? Is it going to go up or down? It's going to go up because we're adding base. So we can fill in our answer here. The pH will go up as we add base, NaOH. This is just a review again of the, the terms. We have our titrant, which is also known as the standard. I'm going to cross out the word titrand because that's irritating. We're just going to call it the sample or the analyte. It is technically called the titrand if you want to learn that, but I find that having titrant and titrand is too confusing. So we're just going to leave that one out for now. Okay? What else do we call a conical flask? We call it Erlenmeyer. What vowels are used in the word Erlenmeyer? All of them are E. Okay, Erlenmeyer flask. The reason that we used a beaker rather than an Erlenmeyer flask when we had this set up is because it makes getting the stirring bar in and out easier, and it makes getting the pH meter in and out easier. Okay? The reason we use a conical flask here is it makes stirring easier when you're stirring by hand. Okay, because if you pick up a beaker and stir, there's likely to be more sloshing about, and you might get spatter. out. So this makes stirring by hand easier. Okay. The equivalence point, the point in the titration in which the amount of the titrant, what's the other word for titrant? Standard. Is that our known or our unknown? That's our known. It's the point at which the amount of titrant added is just enough to completely neutralize the analyte solution. What's another word for the analyte? That is our sample. And is that our known or our unknown? That is our unknown. However, we do know its volume, okay?
If we added it.
Yeah, we put like, say, 10 milliliters in our flask, okay? So it has an unknown concentration, but known volume. So you would use a 10 milliliter pipette to get 10 milliliters of your unknown into your flask. At the equivalence point in an acid-base titration, it does say moles of base equal moles of acid, but it is more true to say that moles of OH minus equal moles of H plus. I think I should get rid of this because it really doesn't do it justice, because what about those 2-to-1 ratios? But the solution contains only salt and water at the equivalence point. There's no acid left, no base left. You have to choose the indicator correctly. If you do choose it correctly, it will change color at the equivalence point. So if you choose it correctly, it changes color when the equivalence point is reached, when the amount of titrant added is just enough to completely neutralize the analyte. The end point is not the equivalence point. Anyone remember what an end point is? End point has to do with the indicator. And if you have trouble remembering that, end sounds kind of like end. Yeah? So endpoint has to do with the indicator. It is the point at which what happens to the indicator. It changes color. I should say it refers to the point in a titration, because we can also call the point at which an indicator changes color the transition point, but that just refers to the indicator. It doesn't have to be during a titration or anything like that. The end point is specifically the point in a titration at which the indicator changes color. So it's either going to be specified by at what pH does it change color, or at what volume does it change color, i.e., at what, actually it should be at what volume does the indicator of titrant, does the indicator change color? This is what a titration curve looks like. We have the pH of the analyte solution. Remember, what is the analyte? The analyte is the unknown, also known as the sample. And then we have the volume of the titrant added. So for example, this might be the pH of the HCl solution. Yeah, thank you. Okay, and then the volume of titrant added, that's going to be the volume of NaOH added. I don't know why I put that in brackets. Let me get rid of that bracket. That makes no sense. Okay, so the analyte HCl, we add we add NaOH to it, and you'll see the pH goes up. But it doesn't go up in just any shape. It goes up in what kind of a shape would you call that? What letter does it look like? Looks like an S. Do you guys know what kind of shape we call that? We call it a sigmoidal curve. It's not next to the power anything curve as far as I know. Okay? Why is it called a sigmoidal curve? Because the Greek letter for S is sigma. And let me tell you, it is refreshing to say that word without getting a bunch of titters. My grade 9s, I told them about the sigmoidal curve, and they thought it was the funniest thing ever. They're like, sigma! I just kind of looked at them like, okay, what would you? 14-year-olds are funny. They're funny little people. And you were one once too, and so was I. We were all funny little people at one point in our lives. Okay, titration of a strong acid with a strong base. Have we done calculations with a strong acid and a strong base when we mix them? We have a quiz on that tomorrow, so hopefully we have. Yes? Okay. So what we're going to do is we're going to start with a strong acid. And if it starts with a strong acid, how would we determine the initial pH? Stoic, yes. Strong. Is this pH going to be high or is it going to be low? It's going to be low. So the initial pH will be low because it's a strong acid. Oh, I got a question for you. Before we go on, we got HCl plus NaOH goes to NaCl plus H2O. At the equivalence point, let's say we started with 0.1 moles here, 0.1 moles here, 0 and 0. Why did I choose 0.1 and 0.1? What would be true when I had 0.1 and 0.1? What point would we be at?
Equivalent.
That would be the equivalence point. Right? Because we've got the same moles of H as we have OH. What would we end up at the end of this reaction? Everything would go down. The reactants would both go down by 0.1. And this would go up by 0.1, and this would go up by 0.1. So 0, 0, 0.1, and 0.1. What is the pH at the equivalence point? 7. Because all we've got left at the equivalence point is sodium chloride and water. Is that salt going to undergo hydrolysis?
No. Wait.
No, because
It's not feel creepy.
it's not feel creepy. And chloride, does chloride hydrolyze? No, why not? Because
Strong.
it came from a strong acid. Okay? So the answer is no. And therefore, the pH at the equivalence point equals 7 when we have a strong titration. Because all you've got is a salt that does not hydrolyze, so it just sits there and does nothing, and you got water, which does nothing to the pH is 7. Is good? So our pH will start low because we've just got acid, and then it's going to go up to pH 7. And it does that fairly quickly. Okay, so it starts low. This is our HCl only. This right here is our equivalence point. After the equivalence point, all the way from point 1 to point 2, which of the two species is in excess? Remember, we have HCl plus NaOH, and this is the one that is added in. So what is the excess reactant as we go from point 1 to point 2? HCl. Does that make sense that HCl is in excess with the pH? The pH is low, yes? And we could do all the calculations for all the different volumes along the way if we wanted to. We're not going to, but you could. Okay? At the equivalence point, the moles of HCl were equal to the moles of NaOH, our moles of H+, equal the moles of OH-. And the only things we have present are, so this was all used up. So we have only products. And that's why our pH, what is our pH at the equivalence point? How would we read that off the graph? pH at the equivalence point, 7. Yeah, if we go across here, And what is happening after 0.3? Or sorry, not 0.3, like dot 3, after 0.3 and 0.4, what species is in excess? NaOH is in excess. If you just saw this titration curve, where would you put the equivalence point? On, like, if you didn't have numbers on the side, right? If there were no numbers here, right? If you didn't have those numbers and you just saw this, how would you describe where the equivalence point goes on that S? It goes in the middle. The equivalence point is always in the middle of the vertical portion. Okay. The equivalence point is in the middle of the vertical portion. Okay, so at 0.1, we had no NaOH added yet, so the pH is low because all we've had is we had HCl reacted with water and all we've got is H3O plus initially. Between 1 and 2, HCl is in excess. 0.2 is just before complete neutralization. So you see how this point is just before complete neutralization? It's still low. And then all of a sudden, once you get to that equivalence point, it just spikes upwards. That's because the pH is a logarithmic scale and it just goes, okay, because you're going by a power of 10 every time you, when you're flipping over from being acid to being base. So yeah. The equivalence point is halfway up the vertical portion of the curve. That is our equivalence point. And that is where we have these guys, the HCl and the NaOH are completely reacted. So you see how they're grayed out? They are all gone. And the only thing we have left is the NaCl and H2O, and that is at the equivalence point. Neither of them hydrolyze. So the solution is neutral, pH is 7. And then we keep adding NaOH. So NaOH is in excess. And so our pH is determined by the fact that we have OH minus. So this is after the equivalence point. By the way, do you guys find that I go too slowly? Do I repeat myself too much? And I'm okay if you do. Think about it. You can give me feedback, like more towards the end of the class. You can think about it. Does she repeat herself too much? Because we're not going to finish this course. And I'm like, should I go faster and repeat myself less when I teach this in the future? That's what I would like to know. So think about it. I'll ask you again towards the end of class. Okay? And if you don't want to tell me, you can just like leave an anonymous note on my desk. Too fast, too slow, like whatever you want. Okay? You're too shy. According to the graph on the left, what is the initial concentration of the HCl solution? You need to think, use your brain to figure that out. Yes. Yes. No. Do you want like a pen, or do you want like a marking pen?
Pen. Thank you.
Okay, so good thing most of you noticed that the pH at the initial concentration was 2. And therefore, you notice that the concentration of the hydrogen ion would be 10 to the negative pH, which would be 10 to the negative 2, which you could always also write if you want to as 0.01. I'm going to do that because it just looks more like a regular concentration. Okay. And that's where most people stopped. What should you do to finish the question?
Oh, right, that's like.
You don't have to write an equation.
Is it equal?
Yes, but you need to say that. Yes? Because it asks what the concentration of the HCl is. Does that make sense? Okay, very cool. So don't forget, go back to the question, see what it asked you for, make sure you have actually answered it. Because it didn't ask you for the hydrogen ion concentration, it asked you for the concentration of HCl. I know they're the same, just write it down. All right, here's another go figure question. What volume of NaOH would be needed to reach the equivalent point? So the volume of NaOH if the concentration of the added base were 0.200 molar. So the concentration of the added base, that's our NaOH, equals 0.200 molar. And we're given some other information here down at the bottom. We are told that the curve that we're looking at, has 50 milliliters of 0.1 molar HCl. So we have the curve shown. $50 milliliters of 0.1 molar HCl. What other information are you given about the curve shown? Go back to the bottom of that diagram and find it. Because I feel like a weakness of many people is not being able to pick information out of like graphs and diagrams given to you. So go look. Yeah. Is there any information on the graph that tells you about the amount of NaOH? Yeah, it reaches the equivalence point at 50 milliliters. Yes? Because our equivalence point is here. And where does it reach it? It reaches it at 50 milliliters. So in order to react 50 milliliters of 0.1 molar HCl, we had to use 50 milliliters of 0.1 molar NaOH. Yes? And now we can look at the question again and say the question says, oh, we're changing something. What volume of NaOH would be needed to reach the equivalence point? And remember, originally we used 50 milliliters of 0.1 molar to reach the equivalence point. How many milliliters would we use if we changed the NaOH concentration to 0.2 molar? And you don't have to do calculations to show it. You can just like think it through. Chat with your neighbor about it.
Also 50 milliliters.
Pardon me?
Add 50 milliliters to equal it.
No, we're still saying that we still have the original 50 milliliters of 0.1 molar HCl. They're asking what would change about this diagram if all of a sudden you made NaOH 0.2 instead of
pH will go up.
0.1. So you've got your same original HCl. What have you done to the concentration? No. What the HCl is the same. Same. The concentration of NaOH, you wouldn't say it would increase because we have told you that it did increase. We're saying, yes, we changed it. So we did one sample of 50 milliliters at 0.1 molar and we got this curve. If we do a second sample of 50 milliliters of the HCl, and now we use 0.2 molar, what would the difference in the curve be? What volume of NaOH would we need to now get there if we change the concentration? So if I say what happened to the concentration, no, we're not adding more HCl. The concentration of NaOH has doubled. Yes? Okay, excellent. What will happen to the volume needed to neutralize all of the HCl if we have doubled the concentration? It'll be half. If you double the concentration, you have twice as many moles in the same volume. If you double the volume, that means you'll have 4 times as many moles. So if you double the concentration, you will need half the volume. Yeah. Would we like to see the math behind that? Anyone? Anyone want to see the math? I'm okay if we don't see the math. You want to see the math? Okay. I'm going to go off on the side, so if you need extra paper, get yourself extra paper. So the math behind it is we have our HCl. We have 50 milliliters, and I'm not going to use sig figs here. Okay, I'm just going to go 50 milliliters of 0.1 moles per liter, and that equals 5 millimoles. Yes? At the equivalence point, how many moles of NaOH must we have? We must have added oh my God, you guys are killing me. What is the equivalence point? It's where you have same moles of H plus and same moles of OH minus. So if I have 5 moles of HCl, which gives me 5 moles of H plus, we also need 5 millimoles of NaOH, which is 5 millimoles of OH minus. Yes? And we were told that originally, the first time, okay, so we got our HCl, we got our NaOH the first time, we had 50 milliliters of 0.1 molar. Is that 5? Yes, it is. Yeah, okay. Okay, so look, we had 5 moles of HCl, and we must have added 5 millimoles of NaOH. How many did we add the first time? We added 5. Yay! That confirms what we predicted. Yes? How much NaOH do we need to add the second time to neutralize it? So the second time, we know that we have 0.2 molar NaOH, and we're like, what volume of NaOH will neutralize all the HCl? How much is all the HCl? 5 millimoles. What volume of 0.2 molar NaOH will neutralize 5 millimoles? Well, if you start with 5 millimoles and you want to say, I don't know how many milliliters, that's what I want to find. What do I need to cancel out? I need to cancel out moles, right? That's going to cancel out my moles. So that's going to cancel moles. Moles leaves me with a milli. And what did I want to find? Milli what? Liters. So I need liters on the top. Do I have my moles per liter? What is 0.2? Moles per liter. So there's 1 liter for every 0.2 moles. So 5 divided by 0.2, you can do that, and you get 25 milliliters, which is half the volume. Now, did you need to go through all of that to get that answer? No, because you can say, I doubled my concentration, therefore I have twice as many moles in a liter, therefore I need half the volume to get the same number of moles. Okay? You can just intuitively do that. You don't need to do all the math to get there. Okay? All right. Let's take a look at the titration of a strong base with a strong acid. So what is going to be different about this setup when we are titrating the base with the strong acid? If we say we're titrating something with something else, which one is the sample and which one is the titrant? Which one is the sample? Which one is the titrant? Which one are we analyzing? When we say with, which one goes in the burette? We are titrating strong base with a strong acid. We're adding the acid to the base.
And the acid is at the.
So we're adding the acid. So when we say with a strong acid, that means we are adding the acid into the base. You need to be familiar with this so you can actually understand. I must be dripping the acid into the base because I am titrating with the acid. I am adding it into the base. So if we look at our picture here, we have our acid and we have our NaOH, we have our strong base. And this picture shows us that we are titrating the base with the acid. Now, usually what this means is usually the analyte, the thing in the flask is the unknown. Okay? It is possible to do it the other way around. When we do our lab in that last week of classes, we'll see that we actually at one point do put the known in the burette. No, so we put the known in the flask and the unknown in the burette, but it's okay. So this is usually the unknown. It is usually the analyte, the sample. And this is our titrant. It is our standard. If we are starting with the strong base down in the flask, what will our initial pH be like? If we are starting with the base in the flask, our initial pH will be high. Okay? Greater than 7. Strong base only. Okay, and then what are we doing as we go along? We are adding in what? HCl, strong acid. But who is in excess? While our pH is still high. Base. Where do we put the equivalence point? Remind me, the equivalence point goes at the middle of the vertical. This is a strong acid and a strong base. What is the pH at the equivalence point? 7. And then, what is making the pH so low down in this yellow section? What is making the pH so low? Yeah, pH is low due to excess HCl. What species do we have at the equivalence point? What chemical species do we have? What chemical species are present? Both acid and base?
Like salt.
Well, we're starting with a solution and we're dripping solution into it.
Yeah.
So is it already in water? Yes. So what do we have left when we get to the equivalence point? We have salt and water. There's no acid, there's no base. These are all gone at the equivalence point. Apparently there's something for you to pick up at the office, if you could just pop down for a minute and go grab it. Yeah. I don't know what it is, Ms. Binding, just. Yeah. Okay, so there we go. We have our pH there, la 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 la. So it's basically just the exact opposite of a weak base, weak, whatever. Yes? Okay, excellent. Could you guys tell me the concentration of the approximate concentration of the base? What would you think that would be? What is the approximate concentration of the NaOH? No, it's fine. Yeah. 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 Okay. How we doing? How would you figure out the concentration of the base? We would find the POH, and then we would find the pH, and then we would find the, or yeah, we would find the POH, and then we'd find the OH, and then that would be the same as whatever. Okay, we're not actually going to do that. We're going to move on. All right, so that was strong, strong. Now we are going to, remember how we did mixtures of strong acids and strong bases, and then we did mixtures of weak and strong. Yes? Weak and strong. So now we are titrating a weak acid with a strong base. Which one are we adding into the other? According to this sentence, which one are we adding into the other? Yeah, we're adding strong base into the acid. And because it is the most famous of all weak acids, acetic acid is going to be our acid, CH3COOH. And that's going to be in our flask. Okay, so if you see our flask, we have our CH3COOH analyte. The analyte is our unknown, also known as the sample. The NaOH is the titrant, also known as the titrant is also known as the known, also known as the standard. I'm going to keep harping on these terms until you know them by heart. So start sticking them in your brain. What does this curve look like in comparison? Like if you just look at this, try to tell me some differences about this curve compared with the strong acid, strong base curve. The equivalence point is not at pH 7. And in this case, it is higher than pH 7. What else is different?
There is like a small spike at the root.
Yeah, there's this weird little hill. There's a hill. What do I mean by hill?
Wasn't there, isn't it? Was that no.
Was there? Let's go look. Where's the hill?
I mean, in the one of
No hill. At the beginning. Is there a hill in the strong, strong one here? Is there a hill? no hill. But when we get into a weak strong, we get a hill. What do you notice about the vertical section? The vertical section is smaller. Kind of has to be. And what do we notice about the initial pH? If concentration of HA, our weak acid, is 0.01 molar, the initial pH there, is it higher or lower than the pH of HCl? Higher initial pH. Ooh. We have the equivalence point. Here, we could also look at the what equivalence point? We could look at the we have an equivalence point and we have a what kind of equivalence point? Half equivalence point. Equivalence point, half equivalence point. What is true at the half equivalence point? Yeah, at the half equivalence point, concentration of H plus is equal to Ka. What is the Ka of this acid? The approximate Ka of this acid is, if we read across, it's about, 4.4-ish. So it would be about, the pH half is about 4.4. Therefore, the pKa is 4.4. Well, approximately, okay, because, we're ballparking it off there. And if the pKa is 4.4, then our Ka is equal to 10 to the negative 4.4, which is 3.98 times 10 to the negative 5, so 4 times 10 to the negative 5. Yes, you could say concentration of H is 10 to the negative 4.4. You could do it this way too, right? It doesn't matter. Either way you get there. Yes? We got 4 minutes left. Can anyone guess What makes the pH at the equivalence point higher than 7? Remember, down here we have excess acid. Up here we have excess base. What do we have at the equivalence point? At the equivalence point, we have only the what? Salt plus water. What is making that pH higher? All we've got is a salt and water. What do salts do to change the pH? They hydrolyze. Yes? So one of the ions will be hydrolyzing. Will it be the anion or the cation that makes it higher than 7?
Most likely.
It is 100% the anion. Cationic hydrolysis always gives you an acidic solution. We have a salt plus water, and the pH is higher than 7. Therefore, the anion must hydrolyze to give OH minus. And that's what's making it slightly basic. And this is why people find this unit, because there's a lot going on. You have to remember neutralization. What do I get at the end of neutralization? I get a salt and water. Normally, you'd be like, salt and water, that's neutral. But what if that salt and water is not neutral? What must be happening? If you have a salt, how can you have a salt that's possibly not neutral? One of the ions has to hydrolyze. If your pH is greater than 7, it has to be the anion, because anions give basic solutions. If it was lower than 7, it has to be the cation, because cations give acidic solutions. We will look at this more next day. Your homework tonight is to study for your quiz. 5.3, 5.4a and b.